Hello, good evening.
Yeah, good evening, sir.
Sorry, Rahulji, there was some delay from my side. I was just traveling,
No, no,
just
it's
reached.
fine. It's fine. It's fine. Okay, then I'll start. Welcome, everyone. This is the live interactive session for Polymer Reaction Engineering class. This session will be discussing a few questions which will be helpful for you in solving the assignments 8. uh, my name is Rohan Jadhav, and I'm the TA for this subject. Starting from the first question, which of the following compounds are considered as chain transfer agents for redox reactions? So first of all, what is the chain transfer? Chain transfer chain transfer agents are introduced inside a reaction which can advance the radical formation by activating the higher state ions and initiating other species. So amongst these, the popular chain transfer agents for redox initiation are methylamine, aliphatic alcohols, and mercaptans. So this is because they are able to initiate the higher state of ions and for other initiating species also by promoting the radical formation. Methylamine is basically it has an amine group where after the dissociation of the removal of the methyl group it becomes a triamine, and that is the exact reason why it is more reactive in creating the chain transfer activities for the redox initiation. And then similar properties are observed in aliphatic alcohol and the mercaptans, which are sulfur-based groups. In the blank suspension polymerization reaction, the polymer is insoluble in its monomer and thus precipitates, contributing to the formation of irregular grains or particles. So here you can see that we have a schematic right here where we have the organic phase and the aqueous phase, and there is an impeller which is mixing the entire mixture. Uh, in the organic phase, monomers come into picture inside the aqueous phase, and the monomer droplets, when they undergo polymerization, it gives rise to the polymer particles. This kind of polymerization process is the suspension polymerization process, where the particles are suspended in a solution. Now, what happens in powder suspension is that the powder suspension polymerization polymer is insoluble in its monomer and thus precipitates, contributing to its irregular grains. So, and in bead polymerization, what happens is in bead polymer is soluble in its monomer and it is smooth and spherical. Hence the name bead. Because beads are smooth and spherical in nature, that's why the polymerization, this branch of suspension polymerization is called bead. So in the powder suspension polymerization, the polymer is insoluble in its monomer and thus precipitates, contributing to formation of irregular. So the answer for this question is powder polymerization. Moving on to the next question. We have two statements here. Statement one says that chain transfer agents and redox initiation are helpful in the case where molecular weight of the product is to be controlled. And statement two is chain transfer agent results in retardation in rate of reaction. Choose the correct answer. So chain transfer reagents, as we have known that they are known to transfer the activity of one active polymer chain to the other in the redox initiation are helpful in the cases where the molecular weight of the polymer is to be controlled. So this is true that whenever the polymer chain is extending in length, we can simply pass on the activity of the extending chain to the other non-extending chain. So with that, we are able to control the molecular weight in the entire initiation process and the polymerization reaction. So statement one is correct. Statement two is that chain transfer agents result in retardation in the rate of reaction. This is also true because Since chain transfer agents are continuously transferring the activity of a single chain to the other chains, the rate of the reaction is quite slow as the activity is being transferred and a single chain is not able to grow to its maximum potential. So that's why statement 1 and statement 2 are correct. The correct option for this question is the first one. In dispersion polymerization usually yields polymer particles with sizes in between those obtained by emulsion and suspension polymerization. The nominal particle size in this range is, so if you have gone through the uh, common description of the emulsion and suspension polymerizations, you will know that the entire range of the emulsion and suspension polymerization lies between micrometers and millimeters, 1 to 10 micrometers and 10 to 100 millimeters. So in these two ranges, the only one which lies is the 1 to 10 millimeters. So that is the correct answer. So the polymer particle yielded will be between the size of 1 to 10 millimeters. So that is the correct answer for this question. The next question is the compounds which absorb the desired amount of photo energy to reach its excitation stage and finally react with the second compound to generate free radical is called photoinitiation. So this is not correct because the correct term for this is the compound which absorbs desired amount of energy and get excited to generate free radicals is called a photosensitizer. So these are not called photoinitiators, they are called photosensitizers. So the desired amount of photo energy is absorbed by the photosensitizer and it starts generating the free radicals. So this statement is false because it's not called photoinitiator, it is a photosensitizer. Kinetic chain length can be defined as the ratio of the following options. So here we have given three options: polymerization rate by initiation rate, polymerization rate by termination rate, initiation rate by termination rate, or none of the above. So first of all, what is kinetic chain length? Kinetic chain length is the number of monomer units reacted with an active center during initiation to the termination state. So from starting from initiation to termination, the number of monomer units which have reacted with an active center give the kinetic chain length during a polymerization process. And this can be written by the expression of rate of polymerization divided by the rate of termination. So that's why correct answer for this question is option B, that is polymerization rate divided by the termination rate. Because all the monomer units which have reacted with an active center during the initiation to the termination is the entire polymerization step. So polymerization rate divided by the final process, which is the termination rate, will give you the kinetic chain length of a polymerization process. In suspension polymerization, the average rate of energy.
Termination only, na? Termination is the correct.
Yeah, yeah,
Polymerization.
termination.
Termination. Okay.
Polymerization, yeah. In suspension polymerization, the average rate of energy dissipation, epsilon, is used to characterize the quality of mixing. In the presence of a dispersed phase, the turbulent intensity blank due to the blank in the velocity fluctuation of continuous phase. Select the correct option. So the mixing phenomena usually controls the particle size density. So the better it is mixed, the higher and better particle size density will be forming. So in suspension polymerization, the rate of dissipation is characterized by the quality of mixing. So the presence of any dispersed phase during the turbulent intensity decreases. The dispersed phase decreases due to the turbulent intensity, and because of in dispersed phase, turbulent intensity decreases due to decrease in velocity fluctuation of continuous. So there are dispersed phase and the continuous phase. So since there are fluctuations in the velocity of the continuous phase, the turbulent intensity the dispersed phase, the turbulent intensity decreases due to the decrease in the velocity fluctuations of the particles. So both terms are decreasing. So that's why the correct answer for this is the fourth option. That is, both of them are decreases and decrease. Dispersed phase, in the presence of dispersed phase, the turbulent intensity decreases due to the decrease in velocity fluctuations of continuous. Which of the following types of monomers cannot be used in plasma polymerization for the formation of cross-linked polymers? Alkanes, cyclic or ring compounds, unsaturated hydrocarbons. So, for a standard polymerization, polymerization process, none of these can be used since they are not suitable to be used with the plasma, as plasma is a very high temperature polymerization reaction, and alkanes, cyclic compounds, or unsaturated hydrocarbons can create unwanted byproducts during the plasma polymerization. That's why compounds which can withstand very high temperatures are only required for the polymerization process. So, none of the above is the correct answer for this. During chain transfer reaction in radical polymerization, the telomerization of polymer occurs. So during chain transfer process, if the rate constant for the transfer reaction is very large, then that of the propagation, while the rate of reinitiation is comparable with the original propagating radical. So in this case, what is happening is when the rate constant for the transfer reaction is very large, then that of the propagation. So it is quickly transferring before it is propagated. So the activity of the chain is transferring before the chain can propagate also, while the rate of reinitiation is comparable with the original propagating radical. So the original radical which was propagating because of the chain transfer, its rate is equal to the reinitiation which is occurring. Reinitiation means formation of new radicals which are initiating the polymerization in other spots. So there will be no effect on the rate propagation itself, but chain length will change drastically and small polymers. Since the chain transfer reaction is very fast, it is not able to propagate properly and it is forming small chains. And because of that, this phenomena is called the telomerization of the polymer. So during polymerization, the chain transfer reaction is very high. At that time, the telomerization process occurs and small polymeric chains are formed. So this happens when the transfer rate is much higher than the propagating rate, and the you can see right here option number B is the correct answer, where KTR, that is the transfer reaction rate, is much higher than the propagation. And we have here Ka is equivalent to the Kp, that is the propagation. So here the initiation radical reaction rate will be equal, reinitiation radical reaction rate is equivalent to the original propagating rate. So that's why option B is the correct answer. KTR is greater than Kp and Ka is equal to Kp. So this is the second option is the correct answer. In radical polymerization, sometimes the premature termination of propagating polymer occurs due to the transfer of hydrogen or other atoms to the propagating polymer from the same molecule, solvent or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to what? So we have four options here. In premature polymerization, one second. So in premature termination of the propagating polymer, which happens, which leads to the decrease in molecular weight of the final product. So there is a decrease in the molecular weight of the final product as compared to the theoretically determined value. So in radical polymerization, if there is premature termination occurring, so the theoretical value of the molecular weight which was expected will not be achieved, and lower value than the theoretical determined value will be formed in the product. So reasons why this happens is because of the transfer of hydrogen and other atoms to the propagating polymer from same monomer, initiator, or solvent. So decrease in the molecular weight of the polymer is the correct answer for this question, since the polymeric reaction rate is reduced. I see that Partha has joined us now, so I'll go through the questions once again. Uh, Sir has observed it, like all the questions. So if you have any other doubt, like sir, if you have any doubts, you can ask me, or else I'll start explaining Partha question.
No problem here. Please go ahead. Because actually I was noting all these things. Only I had one doubt, very specifically with respect to this one only,
Hmm.
where chain transfer agents, like where we are having additional radicals, like free radicals ready to give, right? That only we are considering here.
Huh.
That is the justification for this three, no? Option three options.
Hmm. Okay. Okay then. Yeah, yeah. There are only three options. Yes.
Okay, okay. That much only other things are clear. And the next one is related to, okay, that is polymerization, bead polymerization for
Yeah.
powder suspension and powder related aspects.
Hmm.
Right. Okay, this is clear.
So,
This is clear.
like, if you just go through the sir's notes, right, you will be able to understand all of this, because these are only the process
Yeah,
details.
probably I think here this is for the coming for the upcoming week, I believe.
Yeah, yeah. This is for the upcoming.
Yeah, okay, okay. Otherwise, other things are understandable. Whatever that you have discussed is good.
Hmm. Yes. Okay, then I'll just go through the questions
Shall
once
I
more.
take leave here? Actually, there is one more session
Yeah,
here, if
yeah.
you don't mind.
Yeah, yeah, sure.
Thank you, thank you,
Sure.
thank you.
Yeah. Okay. Okay then. So starting from the first question, which of the following compounds are considered as chain transfer agents for the redox initiation process? So first of all, what are chain transfer agents? Chain transfer agents are agents which transfer the activity of a propagating chain to the other chain. So this happens, and why is this required is because when you want to uh, control the rate of polymerization, and you want to control the molecular weight of the polymer form, this is a very good way to control it, as you won't let the chain to propagate very high at a very high molecular weight, and you can just transfer the activity to the other monomer. So that's why the compounds which are considered as chain transfer agents for redox reactions are amongst these methylamine, aliphatic alcohol, and mercaptans, because they are easily able to transfer the free electrons to uh, other propagating chains. They are very capable in transferring the free electrons, as they themselves are having quite an abundance of electrons which are present there. So that's it. That is the exact reason why the first three are suitable for the redox initiation process. Now, redox initiation process is the initiation process where the polymerization process is initiated relying on free radical producing the oxidation reduction reaction. So that is the redox initiation process. So in that, methylamine, aliphatic alcohols, and mercaptans are used as popular transfer agents for redox initiation. This is a quite normal question, because these are just the few examples of chain transfer agents for redox initiations, and you can quite easily identify them from the electronic configuration and how they are able to transfer the electrons to the other propagating chains. If you read about the chain transfer agents and the redox initiation process. In the blank suspension polymerization, the polymer is insoluble in its monomer and thus precipitates, contributing to the formation of irregular grains or particles. So We know that suspension polymerization has two types, powder and bead. So in so in bead polymerization, what happens is bead polymer is soluble in its monomer and it forms smooth spherical particles. Hence the name bead, because the since it is soluble, it will form smooth particles and it is bead shaped. And since it's not irregular or grain. So the remaining one only is the powder suspension, where the powder is insoluble in its monomer and thus the precipitate contributing to the irregular grains is formed. So that's why powder suspension polymerization is the answer for this question. Statement 1. Chain transfer agents in redox initiation are helpful in the case where molecular weight of the product is to be controlled. As I said in the first question, chain transfer agents in redox reactions are usually used to transfer the activity of one chain to the other, and hence it is able to stop the propagating of the single polymer chain to a very high degree, and we can easily control the molecular weight. Statement 2 is chain transfer agents result in retardation uh, re- retardation in the rate of reaction. This is also true because since the activity of one chain is being transferred to the other, the fastness of the reaction or the how fast the reaction is occurring is also hindered because of this. So that's why the rate of the reaction is also affected in a negative way. So that's why chain transfer agents will result in retardation of the rate of reaction. So statement one is correct and statement two is also correct for this one. Next we have is dispersion polymerization usually yields polymer particles with sizes in between those obtained by emulsion and suspension. So if you know about the emulsion polymerization and suspension polymerizations, we clearly know that emulsion polymerization, the particle size lies between 1 to 10 micrometers, and the suspension polymerization is between 10 to 100 millimeters. So somewhere in the middle of that will be the 1 to 10 millimeters. That is the particle size produced in the dispersion polymerization. So that is in the middle of emulsion and suspension polymerization. You will be able to find the answer for this question just by going through the initial descriptions of the emulsion and suspension polymerization process. So because of this, the correct answer for this is 1 to 10 millimeters. The compounds which absorb the desired amount of photoenergy to reach its excitation stage and finally react with the second compound to generate free radical is called a photoinitiator. So the entire statement is correct except the fact that it is not called a photoinitiator, it is called a photosensitizers. And photosensitizers absorb the desired amount of photoenergy and get excited to generate free radicals. So once reaches the excitation stage, it will start generating the free radicals. So this statement is false because it's not photoinitiator, it is called photosensitizer. Kinetic chain length can be defined as the ratio of. So we have been given three options right here. So first of all, we'll see what is kinetic chain length. Kinetic chain length is nothing but the number of monomer units reacted with an active center during initiation to the termination step. So what happens in this is that if there is an active center and if a monomer reacts with it and subsequently many monomers react with it, and if their activity is monitored from the initiation to the termination, that will give you the and the chain formation how of the monomer, if you are going to judge it, that is the kinetic chain length of that polymerization process. And since that is the definition for the kinetic chain length, from there itself we can point out that the polymerization rate divided by the termination step rate will give you the kinetic chain length of a polymerization process. So option number two, if you can see, polymerization rate divided by the termination rate is the correct answer for this question. In suspension polymerization, the average rate of energy dissipation epsilon is used to characterize the quality of mixing. In presence of a dispersed phase, the turbulent intensity due to the dash in the velocity fluctuations of the continuous phase. Select the correct option sequentially. So in suspension polymerization, what happens is the average rate of energy dissipation is used to characterize the quality of mixing. Now, why do we need to do that? That's because mixing phenomena can control the particle size density. So if you are able to control the particle size density through the average rate of energy dissipation, which is used to characterize the quality of mixing, that will be very helpful in maintaining the molecular weight and controlling it throughout the polymerization system. And because of that, it determines the flow and energy field inside the vessel. So because of this, we are able to easily tell that what is the energy dissipation parameter inside the vessel. So when we, in the presence of a dispersed phase, the turbulent intensity will decrease due to the decrease in the velocity fluctuation of continuous phase. So that is what is happening. So when there is a dispersed phase, in presence of a dispersed phase, the turbulent intensity will decrease, due to the uh, decrease in the velocity fluctuations of the continuous phase. If there is a decrease in the turbulent intensity of the dispersed phase, which can be attributed to the decrease in the velocity fluctuation of the continuous phase. Which of the following types of monomers cannot be used in plasma polymerization for formation of cross-linked polymers? So in plasma polymerization, you need polymers at very high temperatures. In plasma polymerization, uh, the temperature is very high for the cross-linking of polymers which are required. And that is the exact reason why alkanes, cyclic or ring compounds and unsaturated hydrocarbons, which are mentioned right here, cannot withstand that kind of agitation, and they are not suitable for this kind of cross-linking process. So that is the exact reason why none of these are suitable for the uh, reaction, plasma polymerization reaction. During chain transfer reaction and radical polymerization, the telomerization of polymer occurs. Now, first of all, we need to understand uh, here we can see that there are different terms being used here: chain transfer reaction and radical polymerization, and telomerization. Chain transfer, we know what is chain transfer. Chain transfer occurs when the activity of one chain is given to the other chain. The active center of the one chain is given to the other chain to stop the propagation of the first chain. And what is telomerization is that when during the chain transfer process, if the rate constant for the transfer reaction is very large, then that of the propagation, when the chain transfer constant is very large than the propagation, while the rate of reinitiation is comparable to the original propagating radical. So what is happening is that there are two processes here. The chain transfer coefficient, the chain transfer reaction coefficient being very larger than that of propagation, first. And second is that rate of reinitiation is comparable with the original propagating radical. There will be no effect on the rate of propagation, but the chain length will change drastically, and small polymers will the reason why small polymers are forming is the chain transfer coefficient is very high. So it is quickly jumping to the other monomers before it can grow up to a certain length. And that is the exact reason which is called telomerization, which means that it is forming small polymers and it is propagating rapidly. That is called telomerization of a polymer. So when does that happen? When the chain transfer reaction rate is greater than the propagating rate, and the reinitiation rate is equivalent to the propagating radical, original propagating radical. So which can be described by option number B, option B, where KTR is greater than KP and Ka is equal to Kp. In radical polymerization, sometimes the premature termination of propagating polymer occurs due to the transfer of hydrogen other atom to the propagating polymer from the same solvent or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to blind. So in radical polymerization, what happens is the process of premature termination of propagating polymer happens, which leads to decrease in molecular weight of the final product. So the molecular weight is decreased since there is premature termination. The polymer chain is not allowed to grow to its maximum potential. And when this is happening, the theoretical molecular weight, which has been calculated for the radical polymerization process, will cease. Will cease and it won't match with the uh, molecular weight of the product form. Molecular weight of the product form will always be lower than the expected theoretical value because of premature terminations. So, option number four, decrease in molecular weight of polymer, is the correct answer for this question. So, I hope you were able to understand this. You will be reading about these concepts in the upcoming lectures. Uh, Upcoming lectures in the sense like this week's lectures. So here are the few questions which will help you in answering and solving the assignment for this week. So you can go through this, and I'll be, as usual, uploading this back in the YouTube. So from there also you'll be able to access the session number 8, which is today's class. If you have any questions,
Yeah, that's why I was whatever questions he was coming,
hmm,
I was thinking he might be it is from the upcoming sessions like
yes,
week
yes,
week week 9.
hmm.
Actually, I
Because
didn't started week 9 yet. Actually, I'm
okay, okay,
still in week 8. Due to some official work, I could not able to complete the entire week session.
oh no, because the week nine's, I think week 9 has also released the assignment also, right? That's why.
Yeah. Week 9 assignment and week 8, I'm still in week 8 and few portions are left. So
Okay,
hopefully by today I will complete everything.
yeah, yeah. Just complete the week 8 assignment also quickly, so that you will be on track with the current assignment, right?
Yeah.
So if you're going to start solving the week 9 assignments, you can go through this video and you will be
Okay.
able to understand the questions.
Okay. Can I ask one like basic question that was coming in my mind during
Yeah.
when I was going through?
Hmm.
In polymerization, many times it has been said कि continuous will be having individual monomer will get connected and form a chain or step or whatever.
Yeah.
So the entire reaction, whatever the polymerization form we are getting,
Hmm.
that is in the form of molecular weight.
Yes. We
Okay.
characterize
So
that by molecular. Yes.
yeah. So is this a single molecule that has been formed by chain reaction, or it is a uh, hello?
Hello. Yeah. Tell me.
Yeah, can you hear?
Yeah, yeah. I can hear. I can hear you.
Yeah.
I thought you
So
were still speaking English.
or it's a different polymers that is formed in a single molecule, or it's a
No.
single polymer.
Actually, what happens is when polymerization occurs, the end product is actually like the entire mass of the polymer which is formed at the end. It's actually a collection of different chain sizes. So molecular weight is determined based on the longest chains which are present in the polymer mixture.
Longest chain means along with that longest chain, other chain will also be there.
Other chains will be present separately. Like uh, like I said, like you can imagine my fingers as the polymer mixture, the entire polymer mixture. So I have 10 fingers. So you can imagine this as the 10 chains 10 different chains which are forming the entire
in a single
polymer
molecule.
mixture. Yeah, yeah. No, not a single molecule, not a single molecule. The
No,
entire
no, no, no.
polymer mixture.
In a, the precipitation that we are getting.
Hmm. The precipitate which we are getting is composed of these 10 chains.
10 different
This,
chains. Okay.
yeah, not 10, like, yeah, basically 10 different chains.
Yeah, yeah, different
And
means the length will be
yeah,
different, but
length will
having
be different.
same functional group, same kind of uh, polymer
Hmm.
molecule.
Yes. Yeah. So how we decide the molecular weight is amongst this mixture of chains, there will be a molecular weight or there will be a chain length which will be like the longest or the very like longest chain. Longest chain will give you the weight average molecular weight, and the like if the number of chains is repeating, if example you have a single chain of a specific size which is repeating in a very high like in a very high frequency, you can define the molecular weight by that also. So these are the two different methods by which you can define the molecular weight, by
Okay.
number average molecular weight and weight average molecular. So like I think in the first two or three classes I gave some examples where I
Yes,
explained
yes,
the
yes. I
molecular
also
weight.
remember. I also remember.
Yeah, yeah. So I explained the molecular weight properly in that. So if you will revisit that video, you can clearly understand what happens.
Okay.
Yeah.
Mm.
Okay, then I hope you were able to understand that.
Yeah, 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 yeah. That I'll go through first. Uh,
Hmm.
this like coming videos, and
Hmm.
accordingly then I'll solve the questions.
Hmm. Okay, sure. So this video will be uploaded in YouTube soon. Like this week itself, it will be uploaded. So if you're planning to go through this like the week 9 lectures, you'll be able to catch this video on YouTube and you can just solve your problems using this. Okay.
Yeah, yeah, sure.
Okay. Okay then. Uh,
Yeah,
that's all. The class is over. So if
yeah.
you, hmm.
Thank you.
Yeah, yeah. 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 Okay.
Thank you.